Thank you, Cam. So, same picture, a little bit of a variation on the theme. Just a disclaimer. As everyone said today, this is a collaborative project, so a lot of people are involved in putting this work together. Some of their names are there. Talk outline. So I'll just talk about the Stavely Arc and the cover again. How we can get the most out of the data to try and negate that cover, and then what we can do to interpret that data and some conclusions. Okay, so the Stavely Arc was undertaken to better understand the distribution and geometry and geodynamic evolution of the Cambrian Stavely Arc in Western Victoria. As you know, arc rocks are prospective for porphyries and VMS deposits, and as we've seen, only about 3% of the area is exposed Cambrian bedrock. So what tools are available to us to help us see through that cover and solve these problems of looking for the arc, and what can we do to help explorers maximise that? And geophysics is crucial. But there's also quite a bit of control from mapping. Historically, there's been quite a bit of work done, mainly by Ross and Dave, over the Grampians. And you can see on that map there, all those little red dots are field sites where there's a structural measurement. So again, predominantly located around the exposed Cambrian bedrock and the Grampians, which, as you'll hear and probably have heard, that the mapping of the Grampians has played a crucial role in understanding the basement underneath. We also have some drilling, so the 14 stratigraphic holes that we drilled as part of the project in 2014, as well as some earlier VIMP holes, and a whole bunch of company drilling, again, mainly centred around the exposed areas. So I guess the driving force of the work that we've been doing in Western Victoria has been the SEISMIC, the 2009 collaborative seismic transect with GA and Ozscope. So we kind of planned the location of this to have some sort of control at surface, so we could extrapolate down into the section and have some confidence in our interpretations. But in order to then extrapolate away from those areas of control and under the cover, potential field geophysics has played a crucial role. And so we're able to move away from the seismic at depth, as well as interpreting the geophysics to extend our interpretation. So you can see there the Moyston Fault and the Yarramilgit Fault, which mark the boundaries of the zone. So this regional data set comprises... All right, that was supposed to be a little video, but just showing basically the... there we go. The airborne magnetics and gravity have been the two main data sets that we've used to interpolate away from control, and seismic has been a huge help in interpreting those data sets. And in addition to that, we also have various other data sets, including radiometrics, geochem, geochronology, company drilling, and petrophysics. So that's the regional data sets, but if you're interested in sort of prospect size areas or camp areas, obviously the better resolution data, the better resolution of the data, the more you're going to see and be able to interpret from that data set. So here's a data set on the right that was kindly supplied by Navarre over there, Black Range area. And you can see the sort of order of magnitude, a better data set, like the higher resolution data set is basically an order of magnitude better than the regional data. So even when we do some filtering like this, features like these paleo channels really stand out in that data set, and you'd be hard-pressed to try and interpret those in the regional data, as well as things like these faults that really stand out, the Cherry Pool fault, which had previously been inferred, but now it's quite obvious in the high-res data. So how can we squeeze the most out of this data set and gain as much information? Filtering of potential field data is a big part of this. So we use this extensively for the interpretation in Stavely. And you can see on the right here various different filters applied to the data set. So up the top here we have TMI, and then some magnetic filters and gravity in the bottom here. So the filtering was applied to both gridded and profile data, which I'll show a bit later on. And it was also carried out on mag and gravity. And so there's probably about a handful of filters that we found really useful. The ones listed there, the derivatives, wavelength filters were very important, and the tilt filter as well. So here's an example of some wavelength filtering. Now, one of the problems that we have in Stavely, particularly in the south of the project area where we have the newer volcanics, is that the magnetic signal from these basalts overwhelms the deeper sources. So you can see here all this stippled response here from the newer volcanics, and as we apply the bandpass filter, that's removed, and we're seeing the response from these deeper sources, which are the belts. And the same goes for the Rocklands volcanics west of the Grampians. So again, you can see the high frequency response here, and as we move deeper and deeper, we're getting broader wavelength sources, and you can start seeing some of these round features which we've interpreted as intrusives that are below the Rocklands and possibly the source of the eruptions. So the analytic signal is another important filter that we applied. It's good for delineating edges of magnetic bodies, of anomalies, and centres of smaller bodies, but it's also quite relevant in Stavely because we do have remnant magnetism there. So you can see here in the TMI these deep lows that are obviously caused by reverse magnetisation in this case. And if we look at the analytic signal, we can tell that because they come up as mag highs on here. Whereas these bodies in the south here appear to be related and probably some sort of porphyry intrusions or plugs, but obviously they haven't been reversely magnetised. So what else we can do with the data is combine some of these methods. So on the left here is a tilt filter, and this gives us that information from the shallower high-frequency sources. You can see all the newer volcanics in the south are just basically blurring the whole signal. On the right, we have the bandpass, so the deeper sources, longer wavelengths, and we can merge those together to give us a kind of a hybrid effect. So we're still getting the detail from the shallower response, but also we can see the structures beneath that and use that as a good interpretive tool. And we can not only combine magnetic data sets, but also gravity and magnetic. So here we have a high pass gravity image and an RTP surface. So combining those again gives us a data set that we can then use to interpret and kind of see the effects of both data sets. So on to the interpretation. As I mentioned, we concentrated initially in this area in the south of the Grampians, called around the Willora sort of area. Initially that was a project that is potentially still ongoing. And we did some field mapping. So this is the Bushy Creek here, the Stavely Belt, Thursday's Gossens in here, and we did mapping and picked up quite a bit of control in the metasediments that the belts have been thrust into, and we mapped all these structures that hadn't been really identified before, like this fault here, which is the Yarrick fault. So we could see that in the field, and we could also see its effects in the potential field data. So up here you can see that this belt appears to be offset, and if we retro deform that deformation, it appears that the belt lines up quite well and was continuous. And the same in the south here in the Stavely belt. We've got some offsets of the magnetic units, the magnetic volcanics, and if we retro deform it, they line up quite nicely into a single belt. So stepping out from that, we can apply those same observations and then look for them in the regional bigger picture. So looking at the whole Stavely project area, we've gone through and systematically done this interpretation, starting with mapping where the belts are, the distribution of the volcanic belts based on drilling and all the other information we had available. Then we went through and interpreted the Cambrian structures that have emplaced those belts and internally deformed them as well. And then we've identified a whole series of late Silurian and early Devonian strike-slip faults that have deformed those belts and segmented them. And there's also all these intrusives, Devonian and Cambrian intrusives. And I think, as was mentioned earlier, we've come up with a systematic approach to be able to distinguish some of those intrusions based on their orientations and geometries related to the stress field at the time of their intrusion. And there's also some of these later Mesozoic structures that are associated with Antarctica rifting from Australia in the Otway Basin formation. So as well as a qualitative interp, we can do a quantitative interp with the data, and because there is ambiguity in potential field data, it's very important to have some sort of control. So one of the aspects of the Stavely project was to measure the core and run it through a multi-sensor core logger at AGOS at Melbourne Uni, and this is a logger that measures various petrophysical properties of the rock. So you can see we had some mag, sus, density, resistivity, P wave, and natural gamma. So using that data and those constraints and working up some ranges for the petrophysics, we've been able to incorporate that into our modelling, forward modelling for gravity and deep modelling for magnetics. And there is a report that we're in the process of compiling at the moment that will give that will show all that data, and hopefully that'll be out fairly soon. Okay, so part of the quantitative interpretation was dip modelling. So you can see here the Stavely area, and all these black lines represent sections where we've gone and done some magnetic inversion. So we inverted not only on the TMI but also on the first vertical derivative of the TMI, just to have a bit more control on the modelling, and where the TMI was a bit ambiguous and the inversion process wasn't really too happy, we could constrain it a bit more using the TMI. And it also allowed us to separate some closely spaced anomalies and actually invert bodies separately. So out of that came a series of dip estimates for the various belts. Predominantly, most of the belts were dipping to the west. However, there were a few exceptions, and I'll just show a couple of examples. So this is the Dimboola belt up in the north here. We have these radially outward dipping bodies that Ross will probably touch on in his talk next after this. So that's up in the north, and as we go south, we find that the Dimboola belt is dipping predominantly to the east. The Dryden belt, again, predominantly dipping to the east, with some exceptions, like in this vicinity where it's proximal to the moistened fault and has been overturned by thrusting on the moistened fault, and that confirms field mapping, or field mapping confirms the modelling rather, that there are overturned beds and parts of the Dryden belt there. And in the south, again, predominantly west dipping. The blue bodies there are on the Stavely belt, and across the Escondida fault we have what appear to be east dipping bodies in the Narapamaluk belt, which is this one here. So that's actually dipping into the plane of the screen there. So it's a bit of an apparent dip, but again, I think Ross will be talking about that in his talk. So this is just a perspective view of all the dip modelling that we've done. Again, the sections here, and one area that's always been an enigma has been the Black Range region, what's been called the Crab Nebula. So I'll just look at that in a little bit more detail. And we have these three volcanic belts that radiate out from a core of later Devonian intrusion that's buried. And this belt also contains the Eclipse Prospect, Nevada's Eclipse Prospect. So it's had a little bit of work done on it. But if we look at the dip modelling, the Glen Isla belt, again, predominantly dipping to the west, but rather variable, and you can see in the TMI that it's quite internally complex and deformed. So it's giving us a bit of a spread of the dips. The Taiar belt on the west, a lot more continuous anomalies. Again, predominantly dipping to the west. However, in the northern section of it here, where it appears to be truncated and folded, we get a steepening of the dips, and that's that's something that we weren't expecting when I first started out doing this modelling. So it was quite an interesting result. And if we look at the Black Range, Centre Black Range belt in a bit more detail, we can see again predominantly west dipping, but these areas where there's an overturn or looks like overturned bodies and dipping to the east. And again, in the southern part of the belt, we've got this nice fold in the belt, west dipping, and then it swings around to east dipping again. And you can see that nicely in a 3D perspective there. So from the north to the south, we get that nice curvature and change in dip. So all three of the belts are predominantly west dipping. And where we have these folds in the volcanics and abrupt terminations, we also get associated overturns in the dip of the bodies. And so what we've interpreted this is being the result of fault drag deformation along strike slip faults which have deformed the Black Range belts. So this, I guess, has some implications if you're planning a drilling program, particularly for strata-bound VHMS deposits. If you assume that all the belts are going to be west dipping, this is probably a reasonable scenario to plant your rigs on the western side and drill back into the belts. However, if you're unaware of the swing in or the change in the dip and in these areas here you try doing that same approach, you might end up with something like this or intersecting a more than larger amount of mineralisation and give you false reserve estimations. So perhaps something like this might be a better option to go for in these regions, knowing that the dip has been overturned. So the other method that we used was forward modelling of gravity data. We drew a whole bunch of serial sections, 11 serial sections over the entire area. You can see them here, and all the gravity data is the little green dots there. So again, we modelled the sections, our sort of a priori ideas of what the crust was doing based on the seismic and extrapolating out from there. We modelled both a long pass signal for the deeper sources and a shallower high pass signal that gives us high frequency information for the shallower bodies, shallower sources. So we have a little bit more control there, and the complete bouquet as well. And as I mentioned before, this has been constrained by the petrophysics observations and measurements that were made. And we also did some additional detailed sort of smaller modelling, mainly around some of the intrusives, just to get some shape confirmations. So those models were hung in 3D, in GoCAD. The sections were hung in GoCAD, and together with the fault network at the surface, they provided the framework for building the 3D model that you'll hear about shortly. And based on some of that modelling and some of the variations that it presented, we were able to refine the distribution of the Grampians group, for example, particularly in the north, and also vary some of the ideas that we had about the volcanic belts at depth. So in conclusion, regional potential field data is crucial for interpreting the geodynamic understanding of Stavely, and high quality pre-competitive data is available from GADS and through the GSV for free. The modelling of potential field data at a sort of prospect camp scale can be important for drill programs. There is remnant magnetisation in Stavely, so explorers should be aware of incorporating that into their considerations and targeting. And high resolution data obviously is helpful in target identification and follow-up surveys. And finally, the post-mineralisation deformation that we see throughout Stavely at a regional scale is scalable down to outcrop sort of sizes as well. And there'll be some more 3D model action to come shortly. Thank you.